I hope everyone is doing fabulously and is happy and healthy. And so we are going to continue on with our unit of quadratic or polynomial functions. So let's look at the standard and what it's asking you to do. So it's asking you to graph them, and it needs to model a real world situation. So, but we are allowed to also use technology. So this is when you're going to be using Desmos. So if you have not already, put desmos.com, and we're using the graphing calculator, so /calculator. If you have not already opened that up, you need to do so now. But then you are going to identify, describe, and interpret. Let me say that again. Identify, describe, and interpret. Now, identify is pretty easy. Describe is next level. Interpret is the hardest part. And so we're going to be doing several of these together. But the hard part is going to be in the context of the situation. And we're going to look at things such as intercepts, zeros, domain, range, end behavior, maxima, minima, and lines of symmetry. So if you were in the lecture, you received the actual video notes, you received the actual definitions I wanted to use. And it will make this video very, very long if I do so. So I am going to give you the piece that puts it in terms of context, the interpret piece. I still want you to look up the definitions of each of these. So the first thing you need to do is look up these definitions. So just Google them, maybe do like a math definitions vocabulary or math vocabulary intercepts so that you don't get like science, or you don't get other pieces, or just generic. Maybe even put algebra definitions and then type them in. So for the intercepts, what's important to keep in mind when we are interpreting the key features, this is going to be where the x and the y's are 0. Which means in terms of a real world scenario, it's going to be either the start or so when it crosses the 0 for an x value is going to be like a where it lands on the ground. So the y value is going to be the start, but it can also represent the ground. It can represent sea level. It can represent the end. Anything like that. Now, when we're talking about zeros, we're talking about only when it crosses the x. And the important thing with the zeros is recognizing that the number of zeros matches the degree of the function. So if you remember our work from 6.2 last week, the degree is the highest number in the exponent. So if the highest number of the exponent is 3, I would know that there needs to be 3 zeros. So keep in mind, you need to understand that the degree, the highest exponent, tells you how many zeros there are. If you graph something and it doesn't cross the x-axis 3 times, then there needs to be some kind of an explanation for that. And the explanation for that is that some solutions are imaginary. So in the case of an x to the third, we would expect to see 3 zeros. So if this line crosses the x-axis only one time, it is very possible, okay, it's not even possible, it is true that there would be 2, because if it crossed here once, there are going to be 2 imaginary solutions. Now, in regular algebra 2, we ask that you're able to solve for those. In analytical algebra 2, I just need you to understand where that's coming from. I need you to understand that there should be 3, and that the 3 also kind of describes the shape of the graph, but there are not 3 solutions because some of them are imaginary. Domain and range. Domain is always going to be your x values, and your range is always going to be your y values. This is going to kind of tell you like what is realistically happening here. You can see on this first problem, the range for this is all positive numbers. Well, that's because we're talking about honeycombs. And we're talking about hexagons and honeycombs. Well, we can't have negative quantity of honeycomb or a negative number of hexagons. And so that makes sense in a real world situation that the range would be all positive values because we can't have negative ones of those. So the only piece I want you to kind of understand is that the domain and range are going, in real world scenarios, have to kind of define what the real world will look like. If you're talking about temperature, yes, temperature can drop below negative. Can time be negative? I mean, we can have a bad time, but time cannot be negative necessarily. So that should kind of give you an idea as to what to do for that. End behavior. End behavior is super important. I'm going to scroll all the way to the bottom and write some notes down for the end behavior. For the end behavior, you need to know that this is what happens at the end of the line. And that when we have chopped off the end of the line, there's actually this line continues on forever. And so depending upon the equation, this is kind of like that parent function piece that we've been working on for the last 2 weeks, ties into this. So if you know that it's a linear function, it is going to go like this. If it's a negative linear function, it's going to go like this. If it's a quadratic, it's going to go like this. And a negative quadratic is going to go like this. A cubic or a negative cubic to the fourth, a quartic, yes, it looks kind of like a W, and a negative quartic, and then a quintic, or a negative quintic. So what I want you to see is the end behavior. On the end, as we move to the left, it goes down. And as we move to the right, it goes up. So for end behavior, you're always going to have two pieces. You're going to have, as you go to the negative infinity to the left, and then as you go to the infinity to the right, what's happening? And so you always start left and then right. So this one would be down and then up. Well, the negative function is going to be up and then down. For quadratic, you can see that they both go up, up. And for the negative quadratic, they go down, down. Cubic, again, it's going to be down, up. And then up, down. Up, up. Down, down. Down, up. Up, down. Wait, there's a pattern here. Yes, there's a pattern here. All of the even ones, if it's got an even degree, the end behaviors are going to be the same. So it's going to either be up, up, or it's going to be down, down. If it's an odd, it is either going to be down, up, or it's going to be up, down. So you should be able to look at a graph. You should be able to look at a equation and determine the end behaviors. So this is not a difficult thing. But it is something that's very, very important. Okay, maximum and minimum. So these look like, or these are maxima and minima, because, oh wait, that's singular, and minimum is multiple, or vice versa. I can't remember which one's singular. Anyway, maximum means the highest point, minimum means the lowest point. So if the degree is odd, an odd degree, these are always going to be negative and positive infinity. If it's an even degree, there will be a minimum or a maximum. So you could simply say, because this has an odd degree, I know it's going to go to infinity. And that would be an absolutely true statement. And in fact, in the context of the situation, that would totally make sense. Relative maxima and relative minima. That is going to describe where a turn happens. So relative means in this space, so in between, say, these two lines, so in that space, is there a maximum amount? Well, yes. Right here. That is the highest point between these two lines. That is a relative maximum. And I have a relative minimum here in this graph between these 2 points. And you can simply say that in terms of your description. So looking at this graph. So you could say there's a relative maximum between 9 and 12. There's years. There's a relative minimum between 15 and 18 years. There's another relative maximum between 18 and 21 years. And another relative minimum between 21 and 24 years. And the final relative maximum occurs between 27 and 30 years. Those are basically where the turns are happening. And it's just a relationship in terms of what's a shorter space. So we're not looking at the entire graph, we're only looking at small parts. The other piece for these is you need to pay attention to the fact that these numbers are going up, 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 up. So if I'm using a table of values and I see that we're going up, up, and up, and then all of a sudden we start going down, 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 you should be able to look at that table of values and recognize that something happened in there to make it turn. So if you see a table of values going X and a Y, and we start with whatever, it doesn't really matter, -2, -1, 0, 1, 2, 3, 4, 5, and it keeps going. So we are going to look at this and say, okay, it's 0, 2, 7. It's going up, right? You see the pattern. It's not a regular pattern, but it is going up. And then here, it went from 9 down to 5. We should be able to see and recognize that this is going up, 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 and suddenly it went down. And so there is a relative maximum between 1 and 2. Because it was the data points were going up, 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 and then suddenly went down. So if I continue this, it goes 5, 3, so now it's going down. Oh wait, it suddenly went up again. So somewhere between 3 and 4, there is a relative minimum. Because suddenly they were going down, 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 and then now, oop, it's going back up again. I hope this is making sense to you. Okay. And a line of symmetry is basically so that you can fold the line in half. This is only going to occur when we are talking about even functions. Okay, so what am I expecting you to do? Well, number one, I'm going to ask you to go to Desmos and graph this particular function. You can then describe, and a good thing to do would be to describe it in terms of all or most of these vocabulary. What is happening in this problem? So I want you to take a screenshot of the equation or of the function, and then you are going to, so it would include it here, and then where x is the number of rings and f of x is the number of hexagons. So you should recognize that the minimum on this, the minima, is going to be, when you graph this, you can find the dot. It is at 0.5 and 0.25. So x is the number of rings, and y is the number of hexagons. So what this is saying is, based on this function, the lowest number of rings that can occur is a half of a ring. And if there is a half of a ring, then there is going to be a quarter of a hexagon. And that you're not going to find anything less than that. You should be able to say that this graph crossed the y at 1. So it had an intercept, it has a y-intercept at 1. And that makes sense because it says f of x is the number of hexagons. That means we're going to start with 1 hexagon. It's the starting point. We're going to start with 1 hexagon. And if you think about bees, that makes sense. So they start with their 1 hexagon, and then it attaches hexagons all the way around the outside of it. I'm actually not doing too bad of a job doodling this. Aren't I a doodler? Doodle. And here's a ring of hexagons around your 1 hexagon. You can find the solution of anything. So if you have 1 ring, you can actually find out where 1 ring, x is the number of rings, so you can find out if x is 1, then y is what? Well, that would be the number of hexagons, and you can find out that there is going to be 7 hexagons. 1, 2, 3, 4, 5, 6, 7. And that makes sense. So you should be able to take this graph and then describe some pieces of it. Question number 2, when it gives you, or on all of these, when it gives you a solution, first thing I want you to do is graph it, because that's what the first standard says, graph a real world situation with technology, and then we're going to talk about some pieces. So here we're going to talk about what happens when the temperature is 30 degrees. So to do that, we're simply going to do synthetic substitution or synthetic division, which I taught you in the last lesson. The only thing that's tricky about this is we have to put this in standard form first. Standard form means they have to decrease in degree. So this is going to actually be in standard form. The light emitted by a firefly is equal to negative 0.01 t to the third plus 0.4 t squared plus 0.3 t plus 10. When we do synthetic substitution or synthetic division, the 30 goes in the box. That's the number we're going to plug in. And remember, we only write down the coefficients. We bring it down. We multiply up. So we do 30 times the 0.10, which is going to be a negative 0.3. We add straight down. We multiply. We add straight down. We multiply. We add straight down. This is the solution. So if the temperature is 30 degrees, find the light intensity. Well, the light intensity is going to be 109 lumens. For number 3, you're going to do that same thing. You're going to graph it, and then you're going to solve it by substituting it in. And then you have the rest of these questions to answer. So do not forget, you need to look up the definitions in addition to writing whatever else you needed to. And then you need to make sure you are graphing. You don't need to graph number 4, but answering the questions appropriately for each one.